Right now, inside a freezer colder than deep space, a chip the size of a coin is doing something impossible. It holds a particle in two places at once. It entangles two others so tightly that measuring one decides the other instantly, across any distance. And when scientists run the oldest test of reality on this chip, the result keeps coming back the same. The universe has no definite answer until you ask. Tonight we go inside the experiments, the deleted pasts, the split observers, the Nobel Prize nobody wants to explain at dinner. If that pulls you in, hit like and subscribe so the next chapter finds you. Prepare yourselves. We begin. Picture a single atom, cooled to almost absolute zero, floating inside a machine the size of a refrigerator. You fire a pulse of microwave energy at it. You ask it a simple yes or no question. And the atom, instead of answering, does something that should not be possible. It says both, not maybe, not we don't know yet. Both answers fully present, layered on top of each other like two songs playing through the same speaker without blurring. This is the moment a qubit is born. And this is where the old picture of reality, the one most of us still carry around in our heads, quietly fell apart. In your laptop, information lives as bits. Every bit is a tiny switch, on or off, 1 or 0. That is the entire language. Every photo, every message, every video you have ever seen is nothing but trillions of these switches clicking in rhythm. It is a beautifully simple idea, and for almost a century, it described reality well enough that nobody worried about what was underneath. A qubit is different. A qubit is built from something small enough to obey the rules that atoms actually follow. And atoms, it turns out, do not like picking sides. Left alone, an electron does not sit in one spot. It exists as a blurred cloud of possible spots, each one waiting. A photon sent toward two slits does not pick a slit. It passes through both. A qubit, once you put it into this blurred state, can be spinning up and down at the same time, pointing in every direction at once, holding every answer to your question simultaneously. Physicists call this superposition. The name sounds technical, but the meaning is much stranger. The qubit is not hiding its answer. The answer does not exist yet. It will not exist until you measure it. The act of measuring is the moment reality commits. Imagine flipping a coin, except while the coin is in the air, it is not heads and not tails, and not spinning toward one of them. It is a real mixture of both faces, somehow sharing the same metal. You cannot see it. The moment you catch it and open your hand, one face appears. The other vanishes as if it was never a possibility at all. This is how every quantum computer on Earth works. Google's processor, IBM's, the strange glowing chandeliers you see in pictures, dangling wires into vats of liquid helium. Each one of those wires leads to a qubit holding a cloud of answers until a scientist reaches in and forces one to become real. So here is the unsettling part. These machines work. They run. They produce results that match the math every time, which means the weird behavior of the qubit is not a glitch. It is not a measurement error. It is how the world actually behaves when you look closely enough. And if a single atom can hold two truths at once, a question comes knocking that physics has been dodging for 100 years. What exactly is going on when no one is looking? Because the next experiment we're about to walk through suggests the answer is worse than strange. It suggests the electron might not even be there. Follow one electron, just one. Inside a hydrogen atom, it orbits a single proton, and you were probably taught in school that it travels in a neat little circle, like a planet around a sun. That picture is wrong. It was known to be wrong almost 100 years ago, and nobody has been able to replace it with anything comforting. Here is what actually happens. The electron is not in one spot. It is not anywhere specific. What exists, instead, is a fuzzy cloud of probability wrapped around the proton. Thicker in some regions, thinner in others. If you measure, you will find the electron in one place. If you measure again, seconds later, it might be on the opposite side of the atom. Nothing moved it. It did not travel between the 2 points. It simply was here. And then it simply was there. Physicists call this the wave function. Think of it as a weather forecast for a particle. The map tells you where rain is likely, where it is almost certain, where it is impossible. But the rain itself is not there until a drop actually hits your umbrella. Before that moment, there is only the map. For decades, scientists argued about what the map really meant. Einstein was convinced that the electron was always somewhere definite, and the cloud was just our ignorance. He wrote a famous question to a friend. He asked whether the moon is still there when no one is looking at it. For Einstein, the answer had to be yes. The idea that reality blinks into place only when observed struck him as absurd, almost childish. The problem is that quantum computers now let scientists probe this question with a precision Einstein never had. Inside a superconducting chip, a single qubit can be held in that fuzzy state for a controlled amount of time, then tested. When the test is designed carefully, the result does not match the hidden position idea. It matches the cloud perfectly, over and over, which means the electron really does not have a definite location until measured. It has a distribution of possibilities, each one equally real until the universe is forced to pick. Try to sit with that. A chair you sit on is made of atoms. Each atom is a cloud of electrons with no fixed address. The solid feeling under you is not really solidity. It is the pressure of countless probability clouds pushing back against your probability clouds. A kind of mutual agreement to behave like furniture. The world looks solid because there are so many particles involved that the blur averages out. Zoom in on any one of them, though, and the solidity vanishes. You are made of fog holding itself together by habit. Richard Feynman, one of the greatest physicists of the last century, once said that nobody truly understands quantum mechanics. He meant it as a warning. The math works. The predictions are the most accurate in the history of science. But the picture behind the math keeps slipping through our fingers every time we try to grab it, and it is about to slip further, because the next experiment takes a single particle, sends it through 2 doors at once, and catches something looking back. Take a single photon, aim it at a wall with 2 narrow slits cut into it. Behind that wall, place a screen, fire the photon, record where it lands, do it again and again, thousands of times. You would expect 2 bright stripes on the screen, one behind each slit, like the glow under a door. That is what bullets would do. What a thrown baseball would do. Anything solid passing through 2 openings should pile up in 2 matching spots. That is not what happens. The screen fills with a pattern of bright and dark bands, stripes stacked like a zebra. This is the signature of waves, not particles. Ripples passing through 2 gaps spread out on the other side and interfere, cancelling in some places, reinforcing in others. The photon somehow is doing this to itself. A single particle, fired alone, behaves like a wave that split, passed through both slits, and met itself on the other side. This experiment is more than 200 years old in its earliest form. Every first-year physics student has heard of it. What changed recently is that quantum computers can now run a digital version of it, with exquisite control, and they can ask a question the original setup could not. The question is this: what happens if we quietly watch which slit the photon uses? The answer is where things turn unsettling. The moment a detector is placed at the slits, the moment any device records which path the particle took, the pattern on the screen changes. The zebra stripes vanish. 2 clean stripes appear, exactly as you would expect if the photon were a simple particle after all. No wave behavior, no self-interference, nothing strange. Turn the detector off, and the stripes come back. You read that correctly. The particle acts one way when it is observed, and a different way when it is not. Not because the detector bumped it. The effect holds even with the gentlest, most indirect forms of measurement. The variable that matters is whether information about the path exists anywhere in the universe. If it does, the photon is a particle. If it does not, the photon is a wave. When this is recreated on a quantum computer, using qubits in place of photons and logic gates in place of slits, the result is the same. Reality does not let you have both. You can know where the particle went, or you can see interference. Never both. Imagine a door that is either solid wood or open sky, and the only thing deciding which version you see is whether you glance at it. Reach out without looking, and you push through empty air. Glance first, and your hand hits the wood. There is no classical explanation for this. There is no, the photon was always a particle and just got disturbed story that survives the experiment. Physicists have tried. Every attempt has been ruled out, one loophole at a time. So what is the photon really before the measurement? Nobody knows. The math only describes what happens when we look. And the next experiment takes this further. It asks what happens when you let the particle pass through, then erase the evidence of where it went. The result rewrites what you thought cause and effect meant. Here is a trick reality plays. Set up the double slit experiment. Put a detector at the slits, ready to record which path each photon takes. The interference pattern disappears, as expected. Particles, not waves. Now, after the photon has already passed through, before it hits the screen, erase the recording, not delete it from a hard drive. Actually scramble the physical state of the detector so that the which path information no longer exists anywhere, even in principle. You are not hiding the answer. You are destroying it. Watch the screen. The interference pattern comes back. This is called the quantum eraser, first proposed in the early 1980s and built in labs soon after. Quantum computers now run cleaner versions of it with entangled qubits, and the result is rock solid. Erase the record of which path a particle took, even after the particle is long gone, and the particle behaves as if it had been a wave the whole time. Keep the record, and it behaves as a particle. Stop and feel how strange that is. The photon already hit the screen. Its journey is over. Whether it arrived as a wave or a particle should be settled history. But the pattern of arrivals depends on what you do with the evidence afterward. The history of the particle seems to wait for the bookkeeping to be finalized before committing to what happened. Physicists argue about what this means. Some say the past is not rewritten, that what changes is only which subset of results you correlate with which detector. The math works out without time travel. Others point out that even if no information is flowing backward, reality is still refusing to have a single, fixed story until the last measurement is complete. Either way, the comfortable picture of a clockwork universe, where every event is locked in as soon as it happens, does not survive. Think of it like this. You tell a story about your weekend. Halfway through, a friend interrupts and asks a different question. You find yourself telling a different story, not because you are lying, but because the details that matter depend on what the listener is looking for. The quantum eraser suggests the universe behaves this way. The story of a particle is shaped by what question ends up being asked. When this is run on a quantum computer, the erasure happens through a careful sequence of gates that mix and cancel the information stored in a second qubit. The pattern in the first qubit responds exactly as the math predicts. There is no leak, no glitch, no backdoor signal. The deletion of information and the recovery of wave behavior are two sides of the same coin. Here is the part that should bother you. If the universe keeps a record of which path a particle took, the particle is local, solid, ordinary. If that record is scrubbed away, the particle retroactively becomes something else, a spread out possibility again. Reality, it turns out, cares enormously about records, about information, about what can, in principle, be known, which suggests information itself may be more fundamental than matter or energy, a possibility we will come back to. For now, one last twist. If reality responds to whether information exists, then the old dream of hidden, pre-written answers inside every particle faces a very hard test. A test it has now failed. For 30 years after quantum mechanics appeared, many physicists held onto a comforting belief. The weirdness, they thought, was only in our equations. Underneath, particles had real properties, real positions, real spins. We simply couldn't see them. The wave function was a measure of our ignorance, not a description of the world. Somewhere, hidden from view, every particle carried a tiny ledger with its true values written down. This idea is called hidden variables. It was Einstein's preferred escape route. It is also, in a very specific sense, now known to be wrong. The proof came from an Irish physicist named John Bell. In 1964, while working at a particle accelerator in Switzerland, he wrote down a short piece of mathematics that would end up rearranging the foundations of physics. Bell asked a simple question. If particles really do carry hidden instructions, telling them how to behave in any possible measurement, what limits does that put on how strongly two distant particles can be correlated? He worked out the math. He found a hard ceiling. Any theory where particles have local, pre-written properties must obey a specific inequality. Correlations between distant measurements can only get so strong. There is a line they cannot cross. Then he pointed out something explosive. Quantum mechanics predicts correlations that cross the line. For years, Bell's theorem sat as a curiosity, a theoretical result waiting for experiments precise enough to test it. Those experiments eventually arrived. The first convincing ones ran in the 1970s. More sophisticated ones followed in the 80s, 90s, 2000s. Each time, the correlations between entangled particles blew past Bell's ceiling. Each time, the hidden variable picture took another hit. To picture what is being tested, Imagine two friends separated by a great distance, each given a sealed envelope by a mutual acquaintance. They agree that whenever asked one of three questions, they will each open the envelope and read a pre-written answer. If the answers are fixed inside the envelopes before the friends are separated, there are strict statistical limits on how often their answers can match. Bell showed that no matter how clever the writer of those envelopes, no matter how subtle the instructions, correlations in a classical world can only climb so high. Quantum particles, when entangled, match more often than that. Their agreement is too perfect, too tight. Whatever they're doing, it is not being read from envelopes written in advance. So either the particles are communicating instantly across any distance, which Einstein called spooky, and which special relativity forbids for useful signals, or the properties themselves do not exist until measured. Most physicists, faced with those two options, have chosen the second. Particles do not have answers stored inside them. The answer forms at the moment of measurement. The correlations between two entangled particles are not the result of a shared message from the past. They are the result of a shared reality that has no individual pieces at all until someone looks. When this test is performed on quantum computers, the violation is routine. Qubits entangled across a chip match each other at levels that would be impossible if they carried hidden ledgers. The math of Bell is not abstract anymore. It is a daily feature of how these machines run. And recent experiments have closed every escape route that theorists could dream up. Albert Einstein spent the last 30 years of his life at war with quantum mechanics. He never denied the math worked. He was one of the people who built it. What he could not accept was what the math seemed to say about the world. Einstein believed in something he called realism. The belief that objects have properties whether or not anyone is measuring them. A tree in a forest has a height. A planet has a position. Reality does not need an audience. He also believed in locality. The belief that nothing can influence anything else instantly across space. Every effect must ripple outward at or below the speed of light. Combined, these two ideas formed a worldview so obvious that most scientists never bothered to question it. Einstein called this combination local realism. Quantum mechanics, in his eyes, violated both. Particles without definite properties until measured broke realism. Entangled particles that seemed to coordinate across any distance broke locality. He argued, correctly, that if both were true, physics had become something closer to magic. So in 1935, with two colleagues named Podolsky and Rosen, he published a paper meant to expose the absurdity. The paper described a thought experiment. Two particles prepared together, then sent far apart. Measure one, and the other's state seems to be decided instantly, no matter the distance. Einstein believed no reasonable physicist could accept this. Surely, he wrote, there must be hidden variables carrying the information from the start. The paper was brilliant. The reasoning was clean. The conclusion, we now know, was wrong. Bell's theorem, 3 decades later, turned Einstein's thought experiment into a laboratory test. And once the lab results came in, Einstein's preferred picture started losing ground. By the 2010s, experiments had grown so precise that the only way to save local realism was to assume increasingly desperate things. Maybe the detectors were secretly coordinating. Maybe the random number generators choosing the measurements were predetermined. Maybe the scientists themselves were puppets of hidden variables set in motion at the Big Bang. These are the loopholes, and one by one, they were closed. Imagine a courtroom. The evidence against local realism keeps piling up. Every lawyer for the defense proposes a loophole. The detectors are too slow, they say. The photon pairs are too biased. The measurement choices are not random enough. And every time, a new experiment is designed that blocks that specific loophole. The process was slow and meticulous. It took almost 40 years after Bell's theorem to run a single experiment that closed every major loophole at once. When that experiment finally ran in 2015 in 3 different labs on 3 different continents, using 3 different techniques, all 3 got the same answer. Local realism is dead. This is not a philosophical opinion. It is the verdict of the most carefully designed experiments in modern physics. Particles do not have the properties Einstein believed they had. They are not ordinary objects hiding their true values. Whatever is going on, it is something else. Something for which we do not yet have the good word. Einstein did not live to see the verdict. He died in 1955, convinced that someday hidden variables would be vindicated. They were not. 3 groups closed the loopholes in a single year. That is the story worth telling next. 2015 was the year local realism ran out of excuses. 3 laboratories separated by thousands of miles each published the same shocking result within months of one another. Every remaining loophole in Bell's theorem had been closed. There was nowhere left for the classical worldview to hide. To understand what they accomplished, you have to understand what a loophole looks like in this kind of experiment. A Bell test pairs up 2 entangled particles and measures them at distant locations. If the correlations between measurements exceed Bell's limit, local realism is in trouble. But to trust that verdict, you have to trust that the experiment itself was not sneakily classical. There are 3 big worries. The detection loophole, where too many particles are missed, and the ones that get counted might be an unrepresentative sample. The locality loophole, where the 2 measurement sites are close enough that a signal moving at light speed could reach one before the other commits. And the freedom of choice loophole, where the settings of the 2 detectors might somehow be predetermined by some common past influence. For decades, experiments closed one loophole at a time, never all 3 at once. A clever skeptic could always say, sure, you close this gap, but what about the other one? Maybe reality is classical after all, sneaking through the open door. Then, in 2015, everything changed. At the Delft University of Technology in the Netherlands, a team used pairs of electrons trapped in diamond crystals, separated by about 0.8 of a mile across a university campus. At the same time, a team at the National Institute of Standards and Technology in Boulder, Colorado, used entangled photons fired through custom detectors that caught almost every single particle. A third team in Vienna built their own version with yet another approach. Each group's setup was designed to close all 3 major loopholes simultaneously. The random number generators choosing the detector settings were fast enough that no signal could race between the 2 sites. The detection efficiency was high enough that no skeptic could claim the results were skewed samples. The particles were separated far enough that local communication was physically impossible within the timing of the experiment, and all 3 groups saw the same thing. Correlations far above Bell's limit. Local realism violated, with every escape hatch bolted shut. Think of it like a maze. For years, physicists had been trying to trap the classical universe inside a shrinking corridor. Every experiment was a new wall. By the end of 2015, the walls met. There was no corridor left. The classical picture of pre-written, locally real properties simply did not fit the world anymore. Picture a courtroom scene where the defendant has been pleading for decades. Every argument has been patiently countered. Every witness has changed their testimony. Finally, the judge stands, delivers the verdict, and there is no appeal. In 2022, the Nobel Prize in Physics went to 3 scientists whose work made these experiments possible: John Clauser, Alain Aspect, and Anton Zeilinger. This citation quietly acknowledged what the experiments had proven. Entanglement is real. Distant particles really do coordinate in ways no local story can explain. And the weirdness gets worse when you scale it up. Because a quantum computer is not just 2 entangled particles, it is hundreds, bound together. The 2022 Nobel Prize in Physics was given for experiments that had been running in various forms for over 50 years. The official announcement talked about entanglement, about quantum information, about the technology these experiments made possible, like quantum cryptography and the early architecture of quantum computers. What the announcement did not spell out, at least not in plain language, was this. The prize was being given for proving that Einstein's universe does not exist. That sentence sounds like an exaggeration. It is not. The experiments honored by that prize, taken together, rule out any theory of physics where objects have definite properties independent of measurement and where no influence travels faster than light. Both conditions cannot be true. One of them has to go. And once you accept that, the universe you were taught about in school starts to feel like a useful fiction. John Clauser, one of the 3 winners, was a graduate student in the late 1960s when he decided to take Bell's theorem seriously. Most physicists at the time considered it an abstract curiosity. Clauser thought it demanded a real experiment. He built one himself, cobbling together equipment with a colleague, and in 1972 they published the first test. Their results already violated Bell's inequality, though the experiment had loopholes that would take decades to close. Alain Aspect, working in France in the early 80s, built a far more refined version. He used fast switches to change the detector settings while the particles were already in flight, cutting off any possibility of a sneaky signal coordinating the outcomes. His results were cleaner and harder to dismiss. They became the standard reference for a generation. Anton Zeilinger, based in Vienna, pushed the experiments in every direction. Longer distances, more particles, weirder setups. One of his experiments used starlight from distant quasars to set the detectors. The idea being that if 2 galaxies billions of light years apart determined the measurements, no local conspiracy could account for the results. Each of these scientists spent their careers chipping away at the last defenses of local realism, and each came away with the same conclusion. Imagine a scientist trying to prove that the sun orbits the Earth. They build better and better telescopes. They take more and more measurements. With every new instrument, the evidence for heliocentrism grows, and the old geocentric model looks worse. At some point, the verdict is simply in. That is where we are with local realism. The verdict is in. What makes this different from past scientific revolutions is what has not yet been replaced. When Copernicus showed that the Earth moved, we got a new picture. When Darwin showed that species evolved, we got a new picture. Quantum mechanics killed local realism, but the picture of what reality actually is has not arrived. We know what it is not. We do not know what it is. Some physicists think reality is fundamentally non-local. Influences do cross space instantly, but only in ways that cannot carry information. Others think there is no single reality, only branches. Others think the whole story is about information, not particles, and a growing minority thinks the problem is even deeper, that the universe might be a kind of rendered structure, painted into existence as it is observed. To see why, we have to talk about entanglement itself. Take two particles, let them interact, separate them. Send one to the far end of a lab, or across a city, or into a satellite orbiting overhead. Now measure the first one. Whatever value you read, the second one instantly carries a matching or opposite value every time with perfect reliability. This is entanglement. It is not a rumor. It is not a simulation. It has been tested across greater and greater distances for 60 years, and the effect never weakens. In 2017, a Chinese satellite named Mikius split entangled photon pairs between two ground stations separated by more than 700 miles. The correlations held. Other experiments have run across fiber optic cables stretching between cities. The correlations held. There is no known upper limit. As far as anyone can tell, entanglement works across any distance, across the solar system in principle, across the galaxy in principle, across the visible universe if you could set it up. The key word is coordination. The two particles are not sending each other signals. They are not exchanging information at faster than light speeds. If that were happening, relativity would be broken and every other prediction of physics would start collapsing. Careful experiments have confirmed that entanglement cannot be used to send a message. You cannot tap out Morse code this way. Whatever is going on, it is not communication in the normal sense, but it is coordination, tighter than any classical system could produce, faster than any signal could carry, across distances that make the word distance feel inadequate. Picture two coins, minted together, sealed in envelopes, mailed to opposite sides of the earth. You open yours, heads. Your friend opens theirs at the same moment. Tails. Every time. Billions of pairs. Never a mismatch, never a tie, never a wrong correlation. You might think they were just stamped that way at the factory. Bell's theorem says no. The factory cannot explain how tight the coordination is. The correlation, when you measure in certain combinations, is stronger than any factory could arrange in advance. So what is the link? Honest answer, nobody knows. Not really. Some physicists argue that the two entangled particles are, in some deep sense, still one object. The separation you see is an illusion of space. The entangled pair is a single quantum system, and space between them is a kind of stage effect. Measure one, end, and you are measuring the whole thing. Others argue that reality itself is the link. There is no external force coordinating the particles. There is a single underlying description, and what you call two particles are two views of it. Space is a useful way to organize our experience, not a fundamental feature of the system. There is a radical guess too. That entanglement is building space itself. That the reason 2 points feel near each other is that the particles in them are quantumly linked, and distance is just a measure of how strong those links are. Pull the links apart and you pull the space apart. We will come back to this later because it is one of the strangest ideas in modern physics. For now, the point is simpler. Entanglement is real. It reaches impossible distances. And quantum computers do not just use entanglement between two particles, they use it between many. Two entangled particles are strange enough to keep physicists arguing for decades. What a quantum computer does is far weirder. It takes tens of particles, hundreds of particles, sometimes more than 1,000, and binds them together into a single entangled state. This is not a metaphor. The qubits in a quantum processor share one description. You cannot, in general, describe the state of one qubit by itself. The information is distributed across the whole system, held in the pattern of connections between every pair, every trio, every group. Each qubit is less like a marble and more like a thread in a woven cloth. Pull one thread, and the whole pattern shifts. Google's Willow processor, announced in late 2024, has over 100 physical qubits and runs with impressive coherence. IBM has pushed into the hundreds as well. Other groups have entangled more than 1,000 atoms at once in specialized setups. As the numbers climb, the entanglement involves so many combinations that writing it down on paper becomes impossible. The information content of even a modest quantum computer exceeds the storage of every classical computer ever built, if you tried to simulate it exactly. That is why these machines matter. A classical computer asked to track the state of 100 entangled qubits would need more bits than there are atoms in the Earth. Maybe more than there are atoms in the visible universe, depending on the setup. Yet the qubits themselves, sitting inside their cold chamber, track it effortlessly. They are doing, in a small volume of space, something that should be computationally outrageous. Where does the information go? That is the real question. The qubits occupy a region of space the size of a coin. There is no room in that coin for the numbers being tracked. Yet the tracking happens. The calculations produce results. The results are correct. Some physicists say the information is in the correlations, which live in the combined system, not in any one place. Others say the machine is briefly accessing a vast landscape of possibilities, one that is not confined to the chip. Still others say the quantum computer is quietly making use of parallel realities, each handling a piece of the calculation. Those last two answers sound like science fiction. They come from serious researchers at serious institutions. Imagine a musician handed a single instrument. One string, one note at a time, the normal rules. Now imagine the same musician handed an instrument that can play every note simultaneously, with each note in perfect coordination with the others, and somehow the right melody emerges. The sound was never stored anywhere inside the instrument. It was pulled out of a field of possibilities that the instrument briefly touched. A quantum computer, in its best moments, looks something like that. The results are real. The processes are not. What this reveals about reality is uncomfortable. A region of space the size of your fingertip can hold information that, by any classical measure, should not fit. This suggests the universe has more room under the hood than the visible dimensions we experience. Either that, or the information is not being stored in the local chip at all. It is being accessed from somewhere else. Both options are strange. And the next experiment shows just how strange, by letting a decision made now change what happened earlier. The physicist John Wheeler came up with the thought experiment in 1978 that almost nobody believed could be tested. He imagined a variation of the double-slit experiment, where the decision to measure which path a particle took was delayed until after the particle had already passed through the slits. Not delayed by a moment, delayed until the last possible instant, just before the particle hit the screen. The question Wheeler asked was simple. Does the particle decide to be a wave or a particle when it goes through the slits, or does it decide when it arrives? And if the experimenter chooses only at the very end, does that choice somehow reach back and determine what the particle was doing all along? Within a few years, experimenters figured out how to run his thought experiment for real. By the late 1990s, clean versions were being published. By the early 2000s, the delayed choice setup was being reproduced with photons, with atoms, with neutrons, and now with qubits in quantum processors. Every version gives the same answer. The choice made at the end really does seem to determine what happened at the beginning. Think about that for a minute. A photon leaves a light source, it encounters the slits. It crosses a distance toward a screen. Sometime during that journey, perhaps in the last nanosecond, an experimenter flips a switch. If the switch is in position A, the experiment records which slit the photon used, and two bright stripes form on the screen. If the switch is in position B, the experiment does not record the path, and the zebra pattern of interference forms instead. The particle is already deep into its journey when the switch flips. Yet the pattern that forms is not the pattern from a photon that was already a wave or a particle. It is the pattern that matches the choice made after the particle had crossed the slits. This does not mean a signal is traveling backward in time. Most physicists agree that retrocausal language is misleading. The math of quantum mechanics describes it without time reversal. What it does mean is that the particle did not have a definite story during its flight. There was no fact of the matter about whether it was a wave or a particle. The story got written only when the measurement was finalized, and the measurement is what we chose, at the end, to perform. Imagine reading a detective novel where the identity of the killer is not actually decided by the author until you, the reader, reach the final page. Up to that point, there is no killer. The evidence in the earlier chapters does not contradict itself, because it was never specific enough to pin down. As soon as you read the final reveal, the book rearranges so that the evidence now points consistently to the person named. Not retroactively rewritten in any magical sense, simply not committed until committed. Quantum reality seems to behave this way. The consequences are unsettling. Every time a particle crosses a room unobserved, there is no clear story about what it did. The story forms when something, somewhere, finally registers the result. Until then, the past is a draft. And there is a version of this experiment that is stranger still. One where you can erase the evidence after the fact. In the delayed choice experiment, the past is not carved in stone. It is more like wet clay, still workable until the measurement hardens it. For most of science, this sounds heretical. The past is supposed to be fixed. Cause precedes effect. What happened yesterday cannot be changed by what we do today. Quantum mechanics does not break this rule exactly, but it bends it in ways that make physicists uncomfortable. Here is the subtle point. No experiment lets you send a message to the past. You cannot warn your younger self about a mistake. You cannot influence yesterday's stock market. Whatever flexibility the past has in quantum experiments, it cannot be used to change what already happened in any useful way. But the word happened turns out to be slippery. When a photon crosses a region without being recorded, was anything really happening? Physicists now suspect the answer is subtle. Events require records. A particle moving through unmeasured space does not generate a definite history. It generates a spread of possibilities. The history becomes specific only when some part of it leaves a mark that the rest of the universe can read. This is why the double-slit experiment is so jarring. Without a detector, the photon leaves no record of which slit it used. There is no "the photon went through the left slit" story, because there is nothing in the universe that distinguishes that story from the alternative. The absence of a record is not a gap in our knowledge. It is a gap in what actually took place. Quantum computers have made this point sharper by running digital versions of these experiments. In a qubit processor, which path information can be created, stored, or scrambled at will. Each choice changes the interference. The pattern in the final measurement depends on the full informational history of the system, not just the order of events in time. Imagine writing a diary and then, at the end of the day, deciding which events to actually ink in and which to leave as notes. The inked events become the story. The uninked ones float as possibilities that never fully committed. Quantum reality seems to work this way, except it is not you holding the pen. It is the universe itself, deciding which events leave permanent marks based on how they couple to the wider world. The word physicists use for this is decoherence. When a quantum system interacts with enough of its environment, when the photon hits a detector, when a qubit is read by a measurement device, the fuzzy cloud of possibilities collapses into a definite outcome, and the information spreads. From that moment on, the event is real in the ordinary sense. It has become part of the classical world. Before decoherence, there is no clear fact. After decoherence, there is. This has a troubling implication. Most of the history of the universe happened without anyone around to decohere anything. Were those events real? Did stars actually burn in specific places before humans noticed? Most physicists say yes, because stars and dust and planets interact with each other constantly, and all that interaction is itself a form of measurement. The universe is always measuring itself. The need for a conscious observer, in this view, is a myth. But not every physicist agrees, and the next paradox shows why. Take what you learned in the delayed choice experiment. Now push further. What if, after a particle has already been marked, you could erase the mark and see the pattern return? This is the quantum eraser, and it has now been run many times, including in clean digital versions on quantum computers. The setup uses a pair of entangled photons. One is called the signal photon, which passes through the double slit and hits a detector. The other is called the idler photon, which carries the which path information for its partner. If you measure the idler in a way that reveals which slit the signal took, the signal photon behaves as a particle. 2 stripes on the screen. No interference. If you measure the idler in a way that scrambles the which path information beyond recovery, the signal photon behaves as a wave. The zebra pattern of interference reappears. Critically, you can choose how to measure the idler after the signal photon has already hit its detector. The signal is done, gone, registered. Yet the pattern that emerges in the data depends on what you decide to do with the idler later. When this is run on a quantum processor, the entangled photons are replaced by entangled qubits, and the measurements are done with logic gates. You can apply a gate that preserves the which path information, or a gate that mixes it into oblivion. The statistical pattern of outcomes on the first qubit matches exactly what the eraser predicts. Classical reality, where the first qubit has a fixed history regardless of what happens to its partner, is ruled out. Some physicists interpret this as the past being flexible. Others point out that no individual particle is actually changed. What changes is which subset of results you correlate with which detector outcome. The interference pattern shows up only when you sort the data one way. Sort it another way, and the stripes are gone. Either interpretation has the same unsettling feature. The story of what happened to the signal photon is not fully written until the idler measurement is finalized. The universe is, in a real sense, waiting for all the evidence to come in before deciding on a consistent narrative. Imagine a scene where you walk into a room and find a broken vase on the floor. You can later discover, through different investigations, that it was knocked over by a cat, or by a gust of wind, or by a vibration from the street. In a classical world, exactly one of these things actually happened, and the rest are wrong. In a quantum world, until the decisive piece of evidence is registered, the vase's fall has no single cause. Quantum computers let researchers run this experiment over and over, with tighter control than any optical setup. Every run confirms the same result. Information about the past is not just a record, it is part of what made the past what it was. This is why physicists now take information seriously as a fundamental ingredient of physics, on par with matter and energy. Reality does not seem to be made of stuff arranged in space-time. It seems to be made of information, with stuff and space-time as the way that information shows up when we look. And if information is primary, some scientists now argue there may be room for a stranger possibility, that the observer matters more than we have admitted. There is a pattern you start to notice once you have looked at enough of these experiments. The universe does not seem to answer questions that have not been asked. It hands over results the moment you measure, and before that measurement there is no crisp fact hiding just out of view. Some physicists find this ordinary. They say it is how the math works, and the math is fine, and we should stop asking what it really means. Others find it deeply strange. They point out that this behavior is oddly specific. Reality seems to economize. It commits only when forced to commit. It spreads into possibility whenever it is not being pinned down. This is why some researchers have started treating information as the bedrock of physics. The old picture had matter as the foundation. Atoms and forces were real, and information was a human concept laid on top. The new picture, pushed by people like John Wheeler in the late 20th century, flips that. Information is the foundation. Matter is what information looks like when it is being measured. Wheeler coined a phrase for this: it from bit. Every physical thing, he said, owes its existence to yes or no questions, and the answers those questions produce. At first this sounds poetic. It is not. The math of quantum mechanics really does treat information as more fundamental than the particles that carry it. Here is a concrete example. When two particles become entangled, their individual states are lost. You cannot describe one by itself anymore. What survives is the relationship, the information linking the two. The particles are like voices in a duet that have no solo parts, only the harmony. When the entanglement is broken, each particle gets a definite state again. But the information about the old correlations has gone somewhere. It leaked into the environment, or it got measured away. The bookkeeping is strict. Information is conserved in a deep sense, even when it becomes inaccessible to us. Now take this seriously for a second. If information is what the world is made of, and measurement is the act of extracting information, then reality is something like a set of answered questions. The unanswered questions remain as potential, not as hidden facts. The universe is not a warehouse of things. It is an ongoing interview. Picture a library where the books have no content until you open them. The covers are real. The spines are real. The shelves are real. But what is inside each book is undecided until a reader looks at the page. The instant you look, words appear, and they are always consistent with every word any other reader has seen before. But there was no ink in the book when it sat on the shelf. Quantum computers make this interview explicit. Every calculation ends with a measurement, and the measurement is where the answer is born. Before the measurement, the qubits are all the possible answers at once, layered like a chord. After the measurement, one note remains, and the others vanish. This framing troubles some people and exhilarates others. If the universe is built of information rather than stuff, then the hardware running that information becomes a live question. What is the hardware? Is the universe self-hosting, its own substrate, or is it running on something else? That is where the next idea gets very uncomfortable. Because there is a well-known paradox in quantum mechanics that asks whether two observers can disagree about whether a measurement has happened at all. In 1961, the physicist Eugene Wigner proposed a thought experiment. Imagine a friend in a sealed laboratory running a quantum measurement. From the friend's point of view, the measurement gives a definite answer. A photon lands on one detector or the other. The result is written in the lab notebook. Reality, for the friend, has made a choice. Now, from outside the sealed lab, Wigner himself applies the rules of quantum mechanics to the whole room. The friend, the detectors, the notebook, all of it. From Wigner's view, none of it has collapsed. The lab is a superposition of every possible result the friend could have recorded. Until Wigner opens the door, the measurement has not happened for him. For the friend inside, it already happened. Two observers, same event, different realities. This paradox bothered physicists for decades, but for a long time it seemed purely theoretical. There was no obvious way to test it because sealing off a conscious friend inside a fully quantum lab is not possible with current technology. A conscious person is made of too many particles, and they're interacting too strongly with their environment to remain in superposition. Then, in 2020, a team of physicists figured out how to run a version of the Wigner's friend thought experiment, using photons standing in for the friend and for Wigner. The photons played out the roles, measurement devices played out the observers. The results were astonishing. The two observers in the experiment ended up with genuinely inconsistent records of what happened. Not because the experiment was sloppy, because the math of quantum mechanics, applied carefully, predicts that in certain setups, two well-functioning observers will extract different, incompatible stories from the same underlying reality. And when the experiment was run, the predicted disagreement appeared. This is more than a puzzle. It suggests that a measurement outcome is not an absolute event. It is relative to whoever is doing the measuring. Your version of what happened and my version of what happened can both be correct and yet incompatible if we are in certain quantum relationships to each other. Imagine two friends at a party. One of them sees a coin flipped and comes up heads. The other, through a one-way mirror, sees the same coin flipped and comes up tails. Both friends are careful, both are honest, both were watching the same coin. And yet the coin was, in some real sense, both heads and tails until one of them walked outside and told a third friend. Quantum computers allow researchers to set up small-scale versions of this, qubits acting as observers, qubits being observed, measurements done in nested layers. The statistics match what the math predicts. Disagreement between observers is not a bug. It is a feature of how measurement works at the deepest level. This is where things start sounding almost philosophical, but the experiments are real. The data is real. The implication is not that reality is whatever you want it to be, because that would be easy. The implication is far more specific. The notion of a single, shared world that everyone agrees on starts to look like an approximation, useful at human scales, but not exact. If two observers can disagree on what happened, then whose version of the past is the real one? The Wigner's friend paradox, once a curiosity, has now been sharpened into something physicists call an extended Wigner's friend scenario. In this version, there are multiple friends in multiple labs, each running their own measurements, and each of their labs is being observed by a Wigner on the outside. The math shows that if you try to combine everyone's records into a single, consistent story of what happened, you fail. The failure is not sloppy. It is mathematically forced. Under a short list of reasonable assumptions, including that quantum mechanics applies to everything, that observers can use logic, and that there is one shared reality, the records cannot fit together. One of those assumptions has to be dropped. When the extended scenario was run as an experiment in recent years, using entangled photons acting out the roles of friends and Wigners, the results confirmed the prediction. Observers in the experiment arrived at contradictory records of what had taken place. Some physicists take this as a sign that quantum mechanics does not apply to everything. There must be some scale, they say, at which the weirdness stops and classical reality takes over. Other physicists take it as a sign that logic works fine, but there is no single shared reality. Each observer has their own, and reality is stitched together from those local pieces. Still others, the ones who like the math cleanest, say the only assumption worth dropping is the idea of a single world. Every measurement splits reality into branches. Your friend sees heads in one branch and tails in another, and both branches continue to exist, each as real as the other. No contradiction, because the two records live in different versions of the universe. This is the many worlds interpretation, and it used to be the most exotic option on the menu. These days, among working physicists, it is increasingly mainstream. Imagine a river that comes to a fork. Classically, the water picks one channel. In the many worlds picture, the water fills both channels, and each branch becomes its own river, with its own shores and its own history. You feel like you are in one river because you in the other channel is a different version, Just as real, having a different experience you will never know about. Whether or not that picture is correct, the extended Wigner experiments show that something has to give. You cannot have a single, shared, classical reality and quantum mechanics at the same time. The two are incompatible, and one of them is being revealed by experiment to be wrong. Quantum computers are where this will get tested at scale. As processors get larger, they can run nested measurement protocols that more closely approximate the Wigner's friend setup. Someday, perhaps soon, we will see experimental violations of assumptions that seemed unshakable. Each violation will narrow the list of things the universe can be. This is the horrifying part of the story. If we had to pick just one, not that the universe is strange, the strange parts have been known for a century. It is that the idea of a single objective world, the world your parents taught you about and your teachers taught you about and your own senses insist upon, is not, at the deepest level, a good description. Reality is more fractured than that, more negotiable, more observer dependent. And if reality is this flexible, a once fringe idea starts attracting serious attention. The simulation hypothesis used to be the kind of thing you talked about late at night, after a movie, on a couch. You know the pitch. What if all of this, the room, the stars, you, me, is a simulation running on some vast computer somewhere? What if we are characters in a game being played by beings we cannot perceive? For most of its life, the hypothesis lived in philosophy papers and science fiction scripts. Then, starting in the 2010s, a funny thing happened. Real physicists began treating it as a question that might, in principle, be testable. The argument works like this. Suppose the universe is a simulation. A simulation has to cut corners. It cannot render every detail of every atom at all times. No computer, even a civilization level one, can do that. Instead, it should only compute what is being observed, similar to how a video game only renders what the player sees. The parts not being looked at should remain in some compressed, unresolved state. If any effect like this is happening in our universe, it should show up as subtle signatures. Pixelation at some tiny scale, grid artifacts, oddities in how information behaves at the boundaries. Now look at quantum mechanics. Particles do not have definite properties until measured. Reality seems to resolve only when someone or something is checking. Information is conserved with strict accounting. Observers in different frames of reference can disagree about what happened, as if the simulation has not finalized a shared record. And the universe seems to have a smallest unit of length, called the Planck length, below which the very concept of space may stop making sense. None of this proves we are in a simulation, but it lines up uncomfortably well with what a simulation might look like from the inside. Tom Campbell, a former NASA scientist, has proposed a set of experiments meant to test whether reality only renders when observed, much like the rendering in a video game. His experiments are variations on the double slit and the quantum eraser, designed to probe whether the presence or absence of a conscious observer makes a measurable difference. Some physicists consider this approach speculative. Others take it seriously enough to discuss it at conferences. Picture a video game character standing at the edge of a map. Beyond that edge, the game has not drawn anything. There is no forest, no mountains, no sky, because no player is looking that way. If the character could turn and glance over the edge, They might glimpse the flat plane where the world stops being rendered. That glimpse would not prove the world is a game, but it would be strong evidence worth investigating. Quantum experiments keep hinting at something like that flat plane. Properties that do not exist until measured. Histories that do not commit until observed. A universe that seems to respond to being looked at. The simulation hypothesis is not the only explanation for these facts. It is one of several. The many worlds interpretation explains them without any simulation. So does the information first view we talked about earlier. What makes the simulation idea hard to dismiss is that every piece of evidence that would support it is also showing up, one experiment after another, on real quantum hardware. The honest answer is that we do not know yet, and that uncertainty is about to push scientists into their strangest step of all, trying to actually test the simulation idea using quantum computers themselves as the probes. Here is where honesty matters. For all the strangeness quantum computers have uncovered, they have not proven we live in a simulation. Not yet. Perhaps not ever. Every serious physicist working in this field will tell you the same thing. The data is suggestive, it is not conclusive. What quantum computers have proven, beyond reasonable doubt, is that the classical picture of reality is wrong. Particles do not have fixed, hidden properties. Distant particles coordinate in ways that defy local explanation. Measurement plays a role we still do not fully understand. These are not theories anymore. They are experimental results, repeated in hundreds of labs, under every condition scientists can dream up. What quantum computers have not proven is which of several wild explanations is correct. The many worlds view says every possible outcome happens in its own branch of reality. The simulation hypothesis says we are characters inside a rendered structure. The information first view says reality is fundamentally computational, though not necessarily a simulation in the video game sense. Several other interpretations sit on the shelf, each with its own defenders. The experiments cannot, as of today, distinguish between them. Each interpretation predicts the same quantum measurements, because each is built on the same underlying math. What differs is the story told on top. So why bother asking which story is right? Because the stories lead to different predictions at the edges. If many worlds is correct, we might eventually find signatures of neighboring branches through subtle interference effects. If the simulation view is correct, we might find limits on what can be computed, or pixel-like artifacts at the smallest scales of space. If the information view is correct, we might discover that physics itself is a kind of error-correcting code, and scientists have already begun looking for exactly that. Each of these predictions is being chased. Quantum computers are one of the main tools for the hunt. A processor with enough qubits, running the right algorithm, can test whether information behaves the way many worlds predicts, or the way the simulation idea predicts, or something different from both. Think of it like astronomers before the invention of the telescope. They had theories about the stars. Each theory fit the naked eye observations equally well. Only when Galileo turned a lens toward Jupiter and saw 4 moons orbiting it did one theory pull ahead. Quantum computers are the telescope for this question. We are just starting to look. What we already see through the early versions of that lens is alarming. Reality at the quantum level does not behave like a world of solid things. It behaves like a system of information processing, with all the features you would expect from a computation. particles as bits, interactions as gates, measurement as output. The metaphor keeps working every time someone tries to break it. Some physicists say the metaphor is just a metaphor. The universe is not literally a computer. It only resembles one because both obey certain deep mathematical principles. Others say that is exactly what you would hear in a simulation. The characters inside a game cannot prove they are in a game. They can only note that their world keeps behaving in ways consistent with a game. The truth is that we are in a period of genuine uncertainty about the nature of reality. The last time physics was this unsettled was about a century ago, when quantum mechanics was first being born. And a name keeps coming up in these conversations. A name from the 1960s. John Wheeler. John Wheeler was one of the giants of 20th century physics. He worked on the bomb. He coined the term black hole. He trained generations of students who went on to shape the field. Late in his life, he turned his attention to the deepest possible question. What is reality made of? His answer, which he arrived at in the 1980s and 90s, was a phrase that has been whispered in physics departments ever since. It from bit. The physical world, Wheeler argued, arises out of information. Every particle, every force, every event is, at the root, a binary choice, a yes or no, a bit. The word bit here means what it means in computer science, a single binary distinction, on or off, 1 or 0. Every measurement a scientist ever makes reduces at its most basic level to a sequence of bits. Did the detector click? Yes or no? Is the spin up? Yes or no? Did the photon land in this region or that one? Yes or no? All of physics, seen this way, is built from piles of these elementary answers. Wheeler's bold move was to claim that the universe itself is not made of particles that produce answers. It is made of answers. The particles are how the answers are organized. Reality is, at bottom, a network of yes and no. What we call matter is the visible residue of a vast, ongoing computation. When he first proposed this, it sounded mystical. 40 years later, it sounds a lot like standard physics. The field of quantum information has grown into one of the most active areas of modern research. Papers now treat entanglement, coherence, and decoherence as forms of information handling rather than properties of stuff. Some of the deepest insights about black holes in recent decades come from thinking of them as information processors. One of the cleanest examples is what happens when matter falls into a black hole. For years, physicists argued about whether the information about the infalling matter was lost forever. Stephen Hawking originally said yes, it vanishes when the black hole evaporates. Other physicists said no, it cannot be lost, because that would violate the basic rules of quantum mechanics. After decades of argument, the modern answer leans toward the information being preserved, encoded in subtle patterns on the edge of the black hole and in the radiation it emits as it evaporates. In other words, the universe seems to care deeply about keeping track of every bit. Information is treated as a conserved quantity, as fundamental as energy or momentum. You can scramble it, hide it, compress it, but you cannot, in principle, destroy it. Picture the universe as a giant ledger book. Every event gets entered. Entries can be shuffled, copied, spread across many pages. No entry is ever truly erased. If you follow the accounting carefully enough, you can always trace where a bit came from and where it went. This idea has consequences. If information is conserved and fundamental, then whatever the universe is, it behaves like a calculation running on itself, not a metaphor. A literal computation with inputs, operations, and outputs, even if we do not know what the inputs and outputs really are, which raises a specific question. If the universe is computing something, how big is its hard drive? The answer will take us to a place that sounds impossible. In the 1970s, the physicist Jacob Bekenstein made a discovery about black holes that nobody quite knew what to do with. He found that the amount of information a black hole can contain is not proportional to its volume. It is proportional to the surface area of its event horizon. This sounds technical. The consequence is mind-bending. For ordinary objects, we expect information to scale with volume. A bigger box holds more. A longer hard drive stores more bits. Double the size, double the capacity. This is common sense. It is also apparently wrong at the deepest level of physics. Bekenstein's result suggested that the maximum information in any region of space depends only on the area of its boundary, not the volume inside. Stephen Hawking and others developed this further. By the 1990s, a stranger possibility had crystallized. It is called the holographic principle, and it may be the most extreme idea in contemporary physics. The holographic principle says that the three-dimensional world we inhabit, with all its richness, all its matter, all its motion, can be fully described by information encoded on a two-dimensional surface at its boundary. The universe, in its deepest description, is flat. What we perceive as depth, as volume, as space itself, may be a kind of projected image arising from calculations happening on a surface we cannot see. Imagine a hologram on a plastic card. It looks three-dimensional. You can tilt it and see different angles, but the entire image is encoded on a flat layer of tiny scratches. The depth is an illusion of information, not a real extension into space. The holographic principle says the universe might be similar, with all of our three-dimensional experience produced from patterns written on a distant, two-dimensional boundary. There is actual mathematical evidence for this in certain idealized universes that theorists study. It is called the ADS/CFT correspondence, and it shows that a particular kind of three-dimensional universe with gravity is completely equivalent to a two-dimensional description on its boundary without gravity. Every question you can ask inside the volume has a matching question on the surface. Every answer you can compute one way can be computed the other way. The two descriptions are the same physics, dressed up differently. Whether our universe works this way is still unknown. The math works cleanly for certain simplified setups. For our full universe, with its specific shape and its specific expansion, the case is harder to make rigorously. But the guess is taken seriously enough that entire research careers are built around it. This changes the sense in which reality is out there. If the holographic principle is right, the world you move through is a kind of three-dimensional shadow of a flatter, more fundamental reality. You, the room you are in, the planet under you, are all projections. Not in a mystical sense, in a precise, mathematical sense. It also makes the simulation question harder to dismiss. Because if the universe is most naturally described as information on the surface, then reality is, in its deepest description, already a kind of computation. The distinction between physical and simulated becomes blurred, and quantum computers are the first machines that can meaningfully explore this structure, because they too treat reality as information flowing through constraints. In 2019, Google announced that its quantum processor had done something no classical computer could do in any reasonable time. The task was strange and technical. Sample the output of a random quantum circuit with 53 qubits. The Google machine finished in a few minutes. Google estimated that the world's fastest classical supercomputer, had it been set to the same task, would have taken thousands of years. The claim was controversial. Other research groups quickly came up with faster classical algorithms that narrowed the gap. Some argued that the Google advantage was smaller than first reported, but the core result held. For specific tasks, quantum processors can do what no classical machine can match, and the gap grows as the quantum machines get bigger. This moment got a name: quantum advantage. It is the threshold beyond which there is no competitive classical option, and it is a milestone on a longer road. In the years since, other groups have crossed their own thresholds. Chinese researchers demonstrated quantum advantage with photon-based machines. IBM has published results from larger superconducting chips that perform calculations intractable for classical simulation in any practical sense. Quantinuum, using trapped ion hardware, has added its own entries to the list. Every one of these claims gets scrutinized, and some get partly overturned by improved classical methods. But the trend is clear. Quantum computers are pulling ahead on a growing set of problems. The question that has not been fully answered is where the computational power comes from. Think about it plainly. A quantum processor running one of these circuits is not bigger than a small appliance. The chip itself is the size of a fingernail. It holds a finite number of qubits, a finite set of gates, a finite amount of stuff, yet it performs a calculation that would require tracking a number of states greater than the atoms in the visible universe if you tried to do it classically. Where are those states living? How is such a small object handling such a vast computation? The standard answer is that the information lives in the correlations, distributed across the entire quantum state. No individual qubit carries much. The whole system carries an enormous amount, because the number of possible joint states of many qubits grows exponentially with the number of qubits. This is the same math that makes quantum computing powerful. It also raises the question of where, physically, that information is stored. Imagine a single harp string that can somehow play every possible melody at once, each one a distinct vibration, all laid on top of each other until you decide which one to pluck. The pluck gives you one melody. The others vanish. But for the brief moment before the pluck, the string carried an impossible amount of musical information in a length you could wrap around your finger. That is what a quantum computer seems to be doing across many qubits, billions of times a second when it runs. The melody space is vast. The chip is small. The math says the calculation is happening. And nobody can point inside the chip to where the information is physically sitting. This is where physicists split into camps. Some say the information is in the correlations, and that is the end of the story. Others say something much stranger. They say the calculations are happening across parallel realities. When Google released its Willow processor in late 2024, the announcement came with a striking claim from one of its lead scientists. Hartmut Neven, head of the Google Quantum AI Lab, described the machine as performing calculations in a way that lends credence to the notion that quantum computation occurs in many parallel universes. That sentence caused a stir. It is not the kind of thing a major tech company usually puts in a press release. Yet there it was, in a product announcement from a trillion-dollar company. The claim is rooted in the many worlds interpretation of quantum mechanics, which we will get to in more detail in the next chapter. The short version is this. In the many worlds view, every time a quantum system has multiple possible outcomes, all of them actually happen. Each outcome takes place in its own branch of reality. Our familiar world is just one branch, and every other possible history is playing out in its own parallel track. If you take this view seriously, a quantum computer doing a calculation on many qubits at once is not just running a program in one place. It is running pieces of that program in every branch where the qubits took different values. When the machine produces an answer at the end, it is pulling together the results of calculations that happened across the full set of branches. This is why the calculations are so much faster than any single branch computer could manage. The work is being split among many worlds. Nevin's comment was, essentially, that the Google team sees their processor's performance as evidence for this picture. Not proof, evidence. Something that fits the many worlds view naturally, and fits every other view less naturally. Not all physicists agree. There are serious researchers who insist that quantum computers can be fully understood without invoking parallel universes. The math of quantum mechanics, they say, describes what happens. Adding the claim that each possibility is its own world is a story on top of the math, not a requirement of the math. Many worlds is one consistent story. There are others. But the fact that a major industry leader is publicly endorsing the many worlds language is significant. It signals that inside the labs, at least among some researchers, the parallel worlds interpretation has moved from fringe curiosity to serious hypothesis. Imagine you are watching a card trick. The magician deals out every possible hand at once, performs a calculation on each hand in parallel, and then, at the end, collapses all those hands into a single answer in front of you. You might believe the magician is pulling some trick with mirrors. You might believe there is some hidden sleight of hand. Or you might start to wonder whether the deck is somehow real in all those versions at once. Google's machine is, in effect, the magician. And increasingly, senior physicists are saying the third option might be the least crazy. If this is right, then every time your laptop freezes while opening a tab, somewhere out in the branching structure of reality, a version of the tab is opening instantly in a universe where the processor happened to be a quantum one. And that picture only makes sense if you understand where many worlds came from in the first place. In 1957, a young physicist named Hugh Everett, a student at Princeton, submitted his doctoral thesis. In it, he proposed a radical reinterpretation of quantum mechanics. He noticed that the standard picture required two different rules. One rule described how quantum systems evolved smoothly when nobody was watching. Another rule described what happened when a measurement was made. The two rules did not fit together. The measurement rule was clunky, ad hoc, added by hand to account for why definite outcomes appear. Everett asked a simple question. What if the measurement rule is unnecessary? What if measurements are just interactions, no different from any other quantum interaction? What if the apparent collapse of possibilities into a single outcome is an illusion caused by the observer becoming entangled with the system? He worked through the math. He found that if you treat measurements the same way you treat every other interaction, the universe does not reduce to a single outcome. Instead, every possible outcome continues to exist, with the observer entangled with each one. From any single observer's perspective, it looks as if only one outcome happened. From a God's eye view, there are many branches, each one just as real as the others. Everett called this the relative state formulation. Later writers would call it many worlds. The math was elegant. It removed the awkward measurement rule. It made quantum mechanics internally consistent in a way it had not been before. Almost nobody took it seriously at the time. Everett's thesis advisor, John Wheeler, the very same Wheeler from a few chapters ago, found the interpretation uncomfortable and tried to soften its presentation. The broader physics community treated it as a curiosity. Everett himself left physics soon after, worked for the Defense Department on nuclear strategy, and died of a heart attack in his 50s. He lived to see his ideas ignored. Then, starting in the 1970s, many worlds began to come back. As physicists got more serious about quantum information, the interpretation gained defenders. By the 2000s, surveys of working quantum physicists regularly showed many worlds as one of the most popular interpretations, sometimes the most popular. It was no longer fringe. It had become one of the leading ways serious people thought about what is going on. The appeal of many worlds is its minimalism. It assumes only the math. It does not add mysterious collapse events. It does not require consciousness or observers to play a special role. It just lets the equations run, and then admits what they predict. If the equations predict many branches, the universe has many branches. End of story. The cost of the interpretation, of course, is that you have to accept the existence of an unimaginable number of parallel realities, most of which you can never see or interact with. Every version of yourself is real somewhere. Every bad decision you almost made is a life being lived by a twin you will never meet. Imagine a tree. The trunk is the universe at the Big Bang. Every time a quantum event could go multiple ways, the tree grows a new branch. Each branch keeps branching second by second for 13 billion years. By now, the tree is unthinkably vast, with each leaf a world as rich as ours. That is many worlds, and quantum computers, by running calculations in many possibilities at once, may be the clearest practical signature of this picture. But there is one more interpretation, stranger still, that puts consciousness at the center. Hugh Everett's thesis was, when it first appeared, one of those works that the field buries alive. His advisor, John Wheeler, was famous for mentoring some of the brightest physicists of the century, and yet Wheeler discouraged Everett's radical reading. He wrote letters urging him to soften the language. He arranged for the thesis to appear in a trimmed version, with its most provocative claims tucked into footnotes. Everett left academic physics soon after. He went to work for the Weapons Systems Evaluation Group, a Defense Department think tank, where he applied his mathematical gift to nuclear war planning. He became, by all accounts, a heavy drinker and a heavy smoker. He died in 1982, at the age of 51, of a heart attack in his sleep. He did not live to see the shift. Starting in the 1970s, a younger generation of physicists began to rediscover the thesis. Bryce DeWitt, who had been one of the few early defenders, helped popularize the label many worlds. David Deutsch, a physicist at Oxford, made the interpretation central to his thinking about quantum computing. By the 1990s, Deutsch was arguing that quantum computers are only understandable if you accept the reality of parallel branches. The calculations, he said, happen in those branches, and the power of the machine comes from their cooperation. Deutsch is not a fringe figure. He is one of the founders of quantum computing as a field. His 1985 paper laying out the theoretical foundations of a quantum computer is considered one of the seminal works in computer science. When he says the machine exploits parallel worlds, other researchers take it seriously, even if they disagree. Today, surveys of practicing physicists show that many worlds regularly places as one of the top 2 or 3 interpretations, sometimes tied for first with more conservative views. It is no longer a weird idea held by a handful of eccentrics. It is mainstream, at least as mainstream as any interpretation of quantum mechanics can be. The strange part is that accepting many worlds changes how you see the rest of your life. Every decision you agonize over is, in this picture, being made every way possible. Every near miss in traffic is also a collision in a branch you will never see. Every lottery ticket you ever threw away won somewhere. And there are versions of you right now reading this exact transcript under slightly different conditions, with the same face and the same voice, none of whom can reach any of the others. This might sound comforting or terrifying depending on your mood. Many physicists find it neither. They find it mathematically clean. The interpretation simply lets quantum mechanics be what the equations say it is, without any extra collapse rule tacked on. The branches are a consequence of taking the math at face value. Imagine a novelist writing every possible ending for a story, keeping them all, and letting each ending be its own complete book. That is the universe. According to Everett, a library of every variation, each volume shelved next to the others, each one a real and lived world. Quantum computers may be the machines that let us peek at the edges of that library. Not by reaching into other branches, which seems to be forbidden, but by doing calculations whose power only makes sense if the other branches are doing the work too. And from here, one last question pushes quantum mechanics into truly uncomfortable territory. What if the observer, the thing that collapses the possibilities, is not ordinary matter at all? For decades, the measurement problem has sat like a splinter in the foot of quantum mechanics. Measurements produce definite outcomes. The rest of quantum evolution produces blurry superpositions. What counts as a measurement? Where is the line between quantum and classical? Why do macroscopic things seem to obey classical physics, while their parts obey quantum physics? Most physicists answer with decoherence, the process by which a quantum system gets entangled with its environment so thoroughly that the blur washes out into apparent classicality. This works well as an explanation of why big objects look ordinary. It does not fully explain why we, as conscious observers, experience a single definite outcome, rather than a blurry mixture. In the 1990s, Roger Penrose, a Nobel Prize-winning physicist, and Stuart Hameroff, an anesthesiologist, proposed something bold. They suggested that consciousness itself is a quantum phenomenon, and that it arises inside specific structures in the brain called microtubules. Microtubules are tiny protein tubes, part of the skeleton of every cell in your body. In neurons, they are especially important. Penrose and Hameroff argued that these tubes can sustain quantum coherent states, meaning they can hold superpositions of possibilities long enough for those superpositions to play a role in thought. The theory is called orchestrated objective reduction, often shortened to ORC-OR. In this view, each moment of conscious experience corresponds to a collapse of one of these brainscale superpositions. Most neuroscientists dismissed the idea when it first appeared. The brain, they pointed out, is warm and wet and noisy. Quantum coherence is fragile. It requires extreme cold, vacuum, isolation. How could quantum states survive in the tumult of the living tissue? Then experiments started producing surprises. Anesthetics, the chemicals that reliably erase conscious experience during surgery, were found to bind specifically to microtubules. Researchers studied exactly how anesthetics alter the quantum properties of these tubes. The match between ORC-OR predictions and experimental results was unsettlingly close. Lose conscious experience, and the microtubule quantum states are disrupted. Regain consciousness, and the states return. Recent work has pushed further. Laboratory evidence suggests that microtubules can maintain coherence for microseconds at body temperature, longer than the dismissive critics thought possible. Brain scans have even detected patterns that look like entanglement signatures in living neural tissue. The picture is still being argued. Nothing here is settled. But the idea that consciousness might be a quantum phenomenon, once considered borderline mystical, is now being tested in real laboratories with real equipment and real results. Imagine your brain as a symphony. The neurons are the musicians. The classical picture says the music is the sum of their ordinary firings. The ORC-OR picture says that beneath the neurons, at a deeper level, something genuinely quantum is humming. Each conscious moment is a chord being struck in that hidden register, collapsing a cloud of possibilities into the specific note you experience. If consciousness is quantum, a lot of old questions get new teeth. Why do we experience a single reality when quantum mechanics seems to describe multiple? Why does observation seem to matter? Is the observer in these experiments the device, or the mind behind the device? Hartmut-Neven, the Google quantum AI leader, has proposed testing this directly. Hartmut-Neven runs Google's Quantum Artificial Intelligence Lab. He is the person who brought Willow to the world, who has spent decades at the frontier of quantum computing. In the last couple of years, he has started talking publicly about an experiment that even his colleagues find bold. He wants to connect a living human brain to a quantum computer. Not connect in the loose sense. Connect in the precise, physical, quantum sense. His proposal, described in talks and interviews, is to build a system where specific neurons in a person's brain become entangled with qubits in a processor. The goal is to test whether consciousness has a quantum foundation, and if so, whether merging brain and processor produces measurable effects on experience itself. The reasoning runs like this. If consciousness really does involve quantum coherence, as Penrose and Hameroff suggest, then the conscious experience of a person might be modified by entangling their neural qubits with synthetic qubits in a computer. If unified consciousness involves entanglement, as Neven has speculated, then adding external qubits to the entangled network should expand or alter the experience. This is among the stranger experimental proposals in modern science. It lives at the intersection of quantum physics, neuroscience, and philosophy of mind. It also raises questions that most scientists have never had to face. What happens to a person's sense of self when their brain is coupled to a machine? Is the resulting experience still just theirs? Is it something new? Other researchers are working on variations. A startup called Navanic, based in Vancouver, is developing hardware that allows brain signals to interact with quantum systems. Their stated aim is similar: test whether conscious processes and quantum processes are coupled, and if so, what that coupling implies about the nature of mind and reality. None of these experiments have produced confirmed results yet. The technology is at the edge of what is possible. Building the coupling reliably, isolating the signal from ordinary noise, and designing tests that can distinguish quantum contributions from classical ones are all hard problems that nobody has fully solved. But the fact that serious labs with real funding are trying is remarkable. 20 years ago, the idea of testing a quantum theory of consciousness in a laboratory would have been laughed out of most conferences. Today, it is a growing research program. Picture the classic image of someone with electrodes on their scalp, sitting in a medical chair, watching a screen. Now, imagine that the electrodes are not just measuring electrical activity. They are entangling the person's brain at the molecular level with a small array of qubits in a nearby cooled chamber. The person reports on their experience. The researchers record the quantum states. Somewhere in the pattern between the two, if OR or its cousins are right, there should be a signal that consciousness itself has been touched by the machine. If such an experiment ever succeeds, it will be among the most important results in human history. It will also be, for most people, terrifying, because it will suggest that the mind is not a purely biological phenomenon. It is, in some deep sense, a quantum phenomenon, reaching into the same weird fabric that gives rise to superposition, entanglement, and the blurriness of the microscopic world. And that raises an ancient question in a new form. If consciousness is quantum, is there something special about the observer after all? For a long time, physicists tried to chase consciousness out of quantum mechanics. The idea that a mind is needed for wave function collapse was seen as embarrassing, too mystical, a leftover from the early days when even great scientists like John von Neumann considered it. Decoherence seemed to solve the problem by showing that environments collapse superpositions without anyone watching. But the Wigner's friend experiments and the new work connecting quantum states to brain structures have opened the question back up. Not because physicists want to, but because the experiments keep pointing at it. Here is the sharpened version. When does a measurement happen? The easy answer is when a quantum system interacts with enough degrees of freedom in its environment that the superposition loses its interference. This is decoherence. It happens all the time, and it explains why a baseball does not seem to be in two places at once. The hard part is that decoherence does not literally select one outcome. It only makes the outcomes look classical from inside one branch. The other branches are still there, mathematically, in the many-world sense. From any one branch, you see a single result. The others are inaccessible, entangled with environmental degrees of freedom that you cannot untangle. So why do you, the conscious observers, find yourself in one specific branch? Why this one and not another? The math gives probabilities. The experience gives you a specific reality. Where does the transition happen? The philosopher David Chalmers calls this the hard problem of consciousness. It is related, though not identical, to what physicists call the preferred basis problem. Of all the ways a quantum system can split, which splitting corresponds to the actual conscious experiences observers have? The math does not seem to pick one out. Your mind does. Some researchers now argue that consciousness is the feature of the universe that resolves this ambiguity. The observer is not just any interacting system. The observer is the thing that turns a superposition into a felt moment. If that is right, then biology, and specifically the quantum processes inside a conscious brain, play a role in the structure of reality that goes beyond mere record keeping. Not every physicist likes this. Many reject it flatly. But the space for dismissing it has been shrinking as more experiments probe the edges of what measurement means. Imagine a stage with actors arranged in every possible pose at once. The theatre is dark. Nothing is settled. Suddenly, a single spotlight snaps on, picking out one actor in one pose. The other arrangements vanish from view. What is the spotlight? Is it the photons from the bulb? Is it the eye of the audience? Is it something else? Something that only becomes definite when an audience is present to see? Quantum mechanics keeps asking this question, and the answers keep getting more careful. The measurement problem, which was supposed to be solved by decoherence, has come back in a new form. This time, the question is about the relationship between conscious observers and the branches they find themselves in. If consciousness and quantum mechanics really are linked, the implications are profound. Your awareness, reading this, may be a small but real part of how reality commits to one story over another. That is not mysticism. It is a possibility now being tested in labs. And it pushes us back to an older paradox. Why does the universe have a classical side at all? Given how strange quantum mechanics is, there is a puzzle that rarely gets asked in popular accounts. If the microscopic world is a blur of possibilities, why does the everyday world look so solid? Why do tables and chairs and coffee cups not shift between superposed states in front of you? Why does the classical world you actually live in exist at all? The current best answer is called quantum Darwinism. It was developed by Wojciech Zurek, a physicist at Los Alamos, starting in the 1980s and refined over the following decades. The core idea is that the classical world is what survives when quantum information competes to be copied into the environment. Here is how it works. A quantum system, left alone, sits in a superposition. When it interacts with its surroundings, some of its properties get imprinted onto many environmental particles. Those particles carry away redundant copies of the information. Anyone or anything sampling a small portion of the environment can read off the same answer that anyone else would read off from a different portion. The information is broadcast over and over in parallel. The properties that get redundantly copied become the classical properties. The ones that do not get copied stay quantum and fuzzy. The universe, through this process, selects a small slice of possible features to become objectively real, while the rest remain as hidden quantum variables that never enter daily life. The name Darwinism is deliberate. It is survival of the fittest, applied to information. The features that spread widely through the environment win. The ones that do not spread die out of our macroscopic experience. This solves, at least in principle, why everyone agrees that the cup on the table is a cup in that specific place. Information about its position has been copied into so many photons and air molecules that any observer who checks will get the same answer. The cup's position is objectively real in the only sense that objectivity makes sense. It has been broadcast into the shared environment. What has not been broadcast remains invisible. Most of the quantum information in any system never makes it into the classical world. It stays locked in superposition, unavailable to observers, because nothing copied it. The classical world in this picture is a tiny sliver of the full quantum reality, the part that happened to be loud enough to reach us. Imagine walking into a crowded room. Some conversations are so loud that everyone in the room can hear them. Those conversations become part of the shared reality of the room. Other conversations happen in whispers or in languages no one understands, and they never enter the general awareness. They happened, but no one has access to them. Quantum Darwinism says the classical world is the shouted conversations. The quantum weirdness is all the whispers that never made it into the common air. Quantum computers are interesting in this frame because they deliberately suppress decoherence. They keep the whispered conversations going inside their cold chambers long enough to do computation. When they eventually make a measurement, that measurement forces one of the whispered possibilities to become shouted. The answer joins the classical world. This framework helps. It does not, however, dissolve every mystery. It does not tell you why you, as a particular conscious perspective, find yourself in one branch of the broadcasted information rather than another. And it opens a door to an even stranger guess. That space itself, the arena where all this broadcasting happens, is not fundamental. It is built out of entanglement. The newest wave of theoretical physics has started treating space itself, the distance between things, as something built rather than given. The guess is radical. The guess is that entanglement between quantum systems is the fabric of space, and that what we call distance is really a measure of how strongly two regions are quantumly linked. This idea has been growing since about the 2010s, pushed by physicists like Mark van Ramsdonk, Juan Maldatina, and others working at the intersection of gravity and quantum information. The motivation comes partly from a simple thought experiment. If you take a quantum system described on a boundary, the holographic picture we discussed a few chapters back, and you slowly turn off the entanglement between different parts of the boundary, the interior of the corresponding three-dimensional space-time pulls apart. Regions that were close become distant. Eventually, with enough entanglement removed, space itself tears. Physicists read this as a hint. Space is not the stage on which quantum systems dance. Space is the accumulated pattern of their entanglement. Remove the entanglement, and there is no space left to stand in. This is a profound shift. For 300 years, physics has treated space as a given, a container that matter moves through. Einstein refined the picture by showing that space and time are dynamic, warped by mass and energy, but even in general relativity, space-time is the thing, the stuff, the medium. The new picture suggests that space-time itself is made out of something more fundamental, and that something is quantum information. Specifically, entanglement. Here is a concrete illustration. Imagine two regions of space that are very far apart. They contain particles that are not entangled with each other. Now start entangling them, pair by pair. As the entanglement grows, the two regions effectively come closer. Their behavior starts to reflect what you would expect from neighbors. Eventually, if you entangle enough particles, the two regions function as a single connected patch of space with ordinary looking distance between them. This is still speculative. Nobody has turned it into a complete theory of gravity and quantum mechanics working together. But the evidence from simplified models keeps pointing the same way. In the specific mathematical setups that theorists can solve, entanglement and geometry are two faces of the same thing. Quantum computers come in because they can simulate the relevant setups. You can take a pattern of entanglement, run it on a processor, and check whether the behavior matches the predictions of the entanglement equals geometry idea. Early experiments of this kind have already been published. The matches are promising. Imagine a tapestry made of billions of tiny knots. Each knot is a fragment of entanglement between two quantum systems. The way the knots connect determines the shape of the tapestry. What we see as three-dimensional space is the shape that emerges when the knotting is done in a very specific, regular pattern. Change the pattern, and the space changes. Remove the knots, and the tapestry falls apart, taking space along with it. This is one of the most beautiful ideas in physics, and if it is right, it means reality is, at its deepest level, a structured quantum information network. Space, time, matter, all of it emerges from how that network is woven. And there is one related idea so strange that it nearly defies belief, where wormholes and entangled particles are claimed to be the same thing. In 2013, Juan Maldacena and Leonard Susskind, two of the most respected theorists in the world, published a short paper with a startling title and a startling idea. They called it ER equals EPR. And what they proposed, in plain language, was that every pair of entangled quantum particles is connected by a tiny wormhole. Let me unpack the letters. ER stands for Einstein-Rosen, a reference to the 1935 paper by Einstein and Nathan Rosen that first described wormholes as a feature of general relativity. EPR stands for Einstein-Podolsky-Rosen, a reference to another 1935 paper by Einstein, Boris Podolsky, and the same Nathan Rosen, which first described quantum entanglement. Two papers by almost the same authors, published the same year, describing what seemed like two completely unrelated phenomena. One was about geometry, specifically bridges through space-time. The other was about quantum correlations across distance. For almost 80 years, nobody connected them. Maldacena and Susskind proposed that the two papers were describing the same thing. Entanglement and wormholes, they argued, are two ways of looking at the same underlying phenomenon. Every pair of entangled particles is, at the deepest level, linked by a microscopic wormhole, a tiny bridge through space-time that cannot be used to send signals, but that encodes the correlation between the particles. The claim is extreme. It turns one of the most mysterious features of quantum mechanics, the instantaneous correlation of entangled pairs across any distance, into a geometric phenomenon. The particles are correlated because they are actually connected by a hidden geometric structure. The apparent distance between them is not the full story. Under the surface, they are closer than they seem. If this is right, it unifies two of the strangest ideas in physics, and it hints that space-time and entanglement are two aspects of a deeper quantum geometric reality. It also provides a concrete mechanism for the earlier claim that space is built from entanglement. Space exists because of all the little wormhole threads between all the entangled pieces of the universe. Quantum computers have entered this picture in a direct and headline-grabbing way. In 2022, a research team announced they had simulated a small traversable wormhole on a quantum processor. The experiment used a specific quantum code designed to behave like a wormhole, and the processor's output matched the theoretical predictions for how information should move through such a structure. The claim generated debate. Critics pointed out that the experiment did not create a physical wormhole in ordinary spacetime. It only simulated the mathematical behavior. Supporters responded that in a theory where geometry is made of entanglement, the simulation is the wormhole. The two pictures are, by construction, equivalent. Imagine two friends holding the ends of a taut string, standing in a large room. The string connects them even though they are apart. To anyone watching, they look like two separate people with a thread between them. But the thread is the relationship. Without the thread, there is no connection. Scale this picture down to the quantum level, and the thread becomes the wormhole that connects every entangled pair. ER equals EPR is still a conjecture. It has not been proven for our universe, but the research program that it launched is one of the most active in modern theoretical physics. It suggests that reality at the deepest level is a quantum information network, woven from entanglement, with geometry and matter as the shapes that emerge. And if space is built from entanglement, time might be equally fragile. There is no universal clock. That sentence is true in ordinary relativity, where different observers moving at different speeds or in different gravitational fields measure different amounts of time. It is even more true in quantum gravity, where the current best guesses suggest that time itself may be an emergent feature, not a fundamental one. The equation that governs the quantum state of the whole universe, in one prominent approach, is called the Wheeler-DeWitt equation. It was written down in the 1960s by Bryce DeWitt and John Wheeler. The strange thing about this equation is that it does not contain time. It describes a quantum state of the entire universe that simply is, without evolving. This seems crazy. We clearly experience time. Things change, moments pass. How can the equation for the universe leave out the very thing that defines experience? The answer researchers have come up with over decades is that time is relational. It emerges when you look at one part of the universe from the perspective of another. A clock measures time because it is correlated with other systems. A memory records time because it corresponds to changes in those systems. From inside the universe, time feels real because we are embedded in the correlations. From outside, the universe is just a pattern, not a movie. Experiments on small systems have tested this idea. In the late 2010s, a group used entangled photons to demonstrate that time can emerge from entanglement between subsystems. One photon acts as a clock, another as an observer. To an outside measurer of both photons together, nothing changes. To a measurer who looks only at the second photon, conditioned on the first, the second photon appears to evolve over time. The experiment showed explicitly how an apparently timeless underlying description can produce an apparent flow of time for embedded observers. This is a small-scale version of what may be happening in the universe as a whole. Time is not a background parameter that ticks along. time is a pattern of correlation. From inside, the correlation shows up as experience of change. From outside, if any outside existed, there would just be a frozen quantum state with every moment already in place. Picture a film strip. To a projector running it in a dark room, the film looks like a story unfolding frame by frame. To someone standing next to the film reel in the bright light outside, the film is just a roll. Every frame is there, all at once. The time of the story is a feature of how the strip is played, not of the strip itself. Quantum computers let researchers explore these ideas in simulation. They can build small model universes inside a processor, arrange the qubits in different entanglement patterns, and watch how apparent time emerges from different configurations. The results have been consistent with the relational picture. Time, in these toy models, is a consequence of correlation structure. If this is right for the real universe, the implications are dizzying. There is no absolute past. There is no objective present. There is no fundamental flow of time. What we experience is a perspective on a timeless structure, a particular slice of a four-dimensional block, where every moment coexists with every other. This sounds like fatalism. It is not exactly. What it means is that the universe, at its deepest level, may be a static pattern of quantum information, and the feeling of becoming, of flowing time, is a feature of how conscious observers are embedded in that pattern. The pattern itself just is. And beneath all of this, one conclusion keeps surfacing, the one that leaves physicists quietly unsettled. Step back. Look at what has been established, not speculated, but established by quantum experiments to date. Particles do not have definite properties until measured. This has been tested across hundreds of experiments, using every imaginable setup, and the answer never changes. Entangled pairs are correlated in ways no local theory can explain. The loophole-free tests of 2015 closed the last serious escape routes, and the 2022 Nobel Prize sealed the result. The past is not always written in full. Delayed choice experiments, quantum erasers, and more sophisticated variants all show that the history of quantum systems does not commit until the measurement record is complete. Different observers can have inconsistent records of the same event. The Wigner's friend experiments have demonstrated this in the lab, and they put hard constraints on what a shared reality can mean. Quantum computers exploit these features to perform calculations that, by any classical account, are far too large to be happening in the physical chip alone. Put these together, and one conclusion keeps rising to the top. Reality does not have definite observer-independent properties. It is not a warehouse of things that exist, regardless of anyone looking. It is something more fluid, more contextual, more dependent on the act of being probed. This is the horrifying part. Not that the universe is large, which everyone knew, not that life is rare, which is debated. The horrifying part is that the world you see, the solid ground under your feet, the face in the mirror, the people you love, may not be things in the ordinary sense at all. They may be patterns of information that resolve into specific forms whenever something queries them, and that stay as undetermined possibilities when nothing is querying. Most of the universe is unobserved, most of the time, by humans certainly, by other animals sometimes, by instruments rarely. The majority of reality at any given moment is not being checked by anything that could register a classical outcome. What is it doing? Quantum mechanics says in its plainest reading, that those parts of reality are not specific. They are in superposition. They will have definite properties only if and when something interacts with them in a way that forces commitment. This is not a fringe claim. It is what the math of quantum mechanics says, taken at face value. Most physicists, when pressed, will say something like this: the specific solidity of your daily experience is a local effect, produced by the constant measurement that all the matter around you performs on itself. Away from that measurement, reality is less definite than you imagine. Imagine a stage play where most of the scenery is grey fog. As the actors move and interact with specific set pieces, those pieces briefly solidify, catch in the light, looking real. The moment the actors move on, the pieces fade back into fog. The stage is mostly fog, most of the time. The solid moments are the small fraction where interaction is forcing reality to commit. That may be a fair picture of the universe at the deepest level. Solid where observed, diffuse where not. Quantum computers are the first machines that let us hold pieces of the diffuse state in a controlled way and watch what they do. The answer, every time, is that they behave like possibility itself, not like hidden solid things. The solidity only appears at the end, at the measurement. Before that, there is no solid thing hiding. This is what quantum computers have confirmed. Reality, underneath, is not the world you thought you were in. Which brings us back, for the last time, to a child's question. Einstein, in his later years, grew exasperated with quantum mechanics. He told a colleague, reportedly, that he liked to think the moon is still there when nobody looks at it. The remark was half humor, half complaint. He meant that any theory that denied the simple, obvious reality of an unlooked-at moon could not be a complete description of the world. He was asking what seemed like a reasonable question. If the universe is really this dependent on observation, then what happens to the moon when the last person goes to sleep? The question sounds childish. It is not. It is one of the sharpest questions anyone has ever asked in physics, because it forces a choice. Either you say the moon is there, regardless of observation, in which case you are adopting a version of realism that quantum mechanics seems to rule out. Or you say the moon is a complicated enough object that its interactions with everything around it count as constant measurement. So it stays classical and definite without needing a human eye. Most physicists take the second route. The moon is too big, too entangled with sunlight, moonlight, air molecules, the Earth itself. Every moment, trillions of interactions are recording its position. The moon is permanently observed by its environment, and therefore permanently definite. You can sleep, and the moon will still be there in the morning, because the universe has been watching it all night. But this answer, while technically correct, does not quite settle the question. It pushes the weirdness down from the moon to the atoms. The moon is definite because its parts are being measured. The parts are made of particles whose own properties are only definite because of interactions. Go deep enough, and you reach a level where there is no automatic observer, no continuous measurement, and reality really does stay in superposition. The world you live in rests on this deeper layer. The solid moon is a pattern of indefinite particles, whose properties have been forced into consistency by their mutual interactions. Zoom in far enough, and the solidity unravels into quantum fog. Zoom out far enough, and the fog knits itself back into moons and continents and coffee cups. The horror, if you want to call it that, is not that the moon disappears when you look away. The horror is that nothing in the universe exists in the simple, self-contained way you were taught to expect. Every apparently solid thing is a negotiation between quantum parts, a consensus generated by constant interaction. Pull the interactions away, and you are left not with hidden solidity, but with possibilities that have not yet chosen a form. Quantum computers are the instruments that let us study this. For the first time in history, we have machines that can hold pieces of reality in their undefined, pre-measurement state, manipulate them, and watch what happens. The answers come back consistent. Reality at the root is possibility, not substance. The substance is what we see at the top. Where enough interactions have summed into the stable surfaces of daily life, a child asking whether the moon is there when nobody looks turns out to be asking a question that took physics 100 years to begin answering. The answer is subtle: yes and no. Yes, because the moon is interacting with a lot. No, because at the deepest level, there is no freestanding moon at all. There is a pattern of quantum relations that the universe keeps rendering into a moon shape for as long as the rendering holds. This is what quantum computers have confirmed. Not a ghost story, not a simulation proven, but something quieter and stranger. The world is not what you thought. It is a living calculation, and you, reading this, are part of the calculation. The next time you look up at the moon, know that it is looking back. In a sense, everything is entangled, everything is participating. The universe is not a thing, it is an act, and we are just beginning to learn the rules.